Hello everyone, thank you for signing in and watching my live stream. I'm Mr. Matt and this is Dr. Tot. Here you go, Dr. Tot, get a cookie. First of all, thank you guys very much for all the well wishes I got. Last week I was feeling kind of ill, so I wasn't able to stream at all. So I want to pick back up today with some review, just a mixed review of the concepts that we've covered so far. That's going to include the least common multiple, the greatest common factor, problems with factorization, solving conceptually, as well as the rules of exponents. If you have any questions at any point, feel free to let me know. Thank you. Hey, Mark, thank you very much. Thank you for signing in. Excellent. Thank you very much. Thank you for letting me know. I really appreciate the feedback. That helps me a lot. Yeah, I think last time we were having some audio trouble, and then I got the iPad link thing fixed, so I think we're all set to go. So that's really good. And so what I have here is just 11 problems, 11 original problems that we'll go through, and we'll look at different examples. We'll look at those examples, and then I'll manipulate the problems with any time remaining to go through. And as we're going through these questions, feel free to take notes as to which ones you might want to see another example of, because I'll ask for recommendations later. And you can, of course, like as always, if you have any questions, if you're watching this recording, then just drop them in the comments below. Otherwise, you can put them in the live feed chat function, and I'll do my best to answer them. So let's go ahead and get started. Also, just be aware that there is, because it's a live session, there is a little bit of a delay with the iPad, so I'm going to do my best to keep track of that. But if at any point you need me to scroll back, or you missed something, or I'm going too fast, just let me know. I'm just trying to get used to this. So let's go ahead and look at these problems. So the first problem: if 5 raised to the a power times 25 raised to the b power is equal to 125 raised to the c power times 25 to the d power, what is a in terms of b, c, and d? So I'll give you 1 minute, and then I'll give you some hints. I'll give you some hints, and I'm going to give you about 2 more minutes to solve. Okay, so I just want to remind you of some things. I'm not going to solve the whole problem right now. I'm still going to give you some time. But this problem involves the rules of exponents. So remember that in order to use any of the rules of exponents, we have to have common bases. So here the bases are not common. You want to think of a way of rewriting these bases in terms of a common base, so the bases are all even. In other words, is there one number that you can exponentiate, that you can raise to different powers to get 5, 25, and 125? So ask yourself that question, then rewrite those numbers in terms of a common base. Then whenever you have a power of a power, so if you have 2 exponents next to each other, you can multiply. If you're multiplying values raised to common that have common bases, you can add the exponents. Once you get that simplified, and I'll do this step by step with you, but once you get that simplified to a point where you have one base raised to an exponent equals another base raised to another exponent on one side, on either sides of the equal sign, you can drop the bases and equate the exponents. Now here, the question is asking, what is A in terms of B, C, and D? That's just a real tricky way of isolate for A, of asking you to isolate for A or get A by itself. So I'm going to give you 2 more minutes, and then I'll go through about half of the, I'll go through the solution. Okay, so first of all, let me just start you off. When we are looking at these bases, we have 5, 25, 125, and then again 25. So all the bases are not common. They're not the same number. That means we can't use any of the rules of exponents as the problem is written. So we want to rewrite these bases so that they're common. So, for example, is there a number that we can exponentiate or raise to different powers that would equal 5, 25, and 125? And the answer is yes. So 5 to the first power is 5, 5 squared is 25, and 5 cubed is 125. So wherever I see 25, I'm going to substitute in, within parentheses, 5 squared. Wherever I see 125, I'm going to substitute within parentheses 5 cubed. Then we'll have all common bases, and then we're allowed to use the rules of exponents as we know them. So 5 to the a power is fine. That already has a base of 5. But instead of 25, I'm going to write 5 squared. Notice that I'm putting it in an additional set of parentheses there, because that's key. And that could be. That's the pitfall for a lot of SAT problems, especially when there's a negative sign outside of a set of parentheses. They really like to bring that up because students forget to distribute the negative sign throughout the parentheses, and especially if you don't even put the parentheses there. So that's why, when in doubt, just put an extra set of parentheses. 125 we can rewrite as 5 cubed. So we have 5 cubed quantity raised to the c power, and that's times, instead of 25, we'll say, again, 5 squared. And that's going to be quantity times the d power. So now you have powers of powers within these parentheses. So let's go ahead and evaluate those guys. Again, 5 to the a is just going to carry through. 5 squared quantity raised to the b power is going to be equal to 5 to the 2 times b power, or in other words, 5 to the 2b power. 5 cubed quantity raised to the c power is going to be equal to 5 raised to the 3 times c power, which is the same thing as 5 to the 3c power. And 5 squared quantity raised to the d power is the same thing as 5 to the 2 times d power, which is 5 to the 2d power. Now you have common bases, so we can use the rules of exponents. When we multiply, we add the exponents. That'll get you to a point where you have one value on one side and one value on the other side of the equal sign. You can drop the bases and equate the exponents. So I'll give you one more minute. Remember that what is A in terms of B, C, and D means isolate for A. So once you drop the bases, just isolate for A on one side. The whole expression that includes the variables B, C, and D on the other side will be your answer. Okay, I'll give you 1 minute. Okay, so when we multiply, when we're multiplying common bases raised to exponents, we can keep the bases and add the exponents. So 5 to the a times 5 raised to the a power times 5 raised to the 2b power is going to be equal to 5 raised to the a plus 2b power. And 5 raised to the 3c power times 5 raised to the 2d power is going to be equal to, keep the base 5, add the exponents, 3c plus 2d. Now we have common bases on opposite sides of an equal sign. So we can drop the bases and equate the exponents. So we know that a plus 2b has to be equal to 3c plus 2d. And now the goal is just to get a by itself. So I'm going to subtract away 2b. So a is going to be equal to 3c plus 2d minus 2b. And it doesn't matter which order you place them. This is the same thing. You know, it could have been 2d minus 2b plus 3c, or negative 2b plus 3c plus 2d. Any combination of those, of that order, of those orderings, I should say, would be acceptable. And they could present them in any of those ways too. You have to be able to recognize that all three of those versions are equivalent statements. Okay, if you have any questions, please let me know. Otherwise, let's go on to, just to be clear, any version of these are your answers. Okay, number 2. We're evaluating some exponents here with some real bases. We don't have variables any longer. And you're going to leave your answer in exponential form. So I don't need you to calculate the exact numeric value. I just need you to simplify the expression completely into one exponential form. So what is the value of, and this is a complex fraction, the numerator is 3 raised to the 5th power times 9 raised to the 3rd power, quantity raised to the 3rd power, whole thing divided by, this denominator is 27 squared times 3 cubed quantity squared. So you're going to simplify this expression into one exponential form. Okay, I'm going to give you 2 minutes and then I'll start you off in a few steps. And I'm sorry, it slipped my mind to be keeping track of time in the right-hand corner, so I will keep track of time from this point forward. My apologies. Okay, so just like the last problem, we don't have all common bases. Remember, that's the number one thing that you need to recognize when dealing with an exponential problem, when you're trying to, when you're asked to simplify an exponential problem. Here, you can't use any of the rules of exponents until the bases are the same. So, can we write a number in terms of different powers to equal 3, 9, and 27? The key, if you look out for the smallest number, because the smaller number can exponentiate into larger numbers. The larger number isn't going to exponentiate into smaller numbers, right? Because that would be rooting or exponentiating to a fraction, to a number in between 0 and 1. That would do that too. But regardless, if you look at, with these problems, the test makers write these problems that oftentimes the smaller base is the key to unlocking everything else. So notice that 3 to the 1st power is 3. 3 squared is 9. 3 cubed is 27. So we can rewrite all of the bases in terms of a base of 3. So 3 to the 5th is fine, so I'm just going to leave that alone for now. But 9 I can write as 3 squared. Notice I'm writing it inside of a new set of parentheses. I'm inserting more parentheses because of that. Now this is still raised to the 3rd power, so don't forget that extra, that cube that was in the original problem, the original exponent. This whole thing now is still cubed. And then this is quantity divided by, now 27 I can rewrite as 3 cubed, and then that's still raised to the 2nd power. And 3 cubed is fine, so we can leave 3 cubed alone. Now this whole thing, though, is still squared. Now let's take care of the powers of the powers. So when we have a power of a power, we can multiply. Again, the 3 to the 5th is fine. It's just going to follow along for now. But 3 squared quantity cubed, that's the same thing as 3 raised to the 2 times 3 power, which is 3 to the 6th power. And then this thing is still all raised to the cubed power. Quantity divided by 3 cubed quantity squared is the same thing as 3 to the 3 times 2 power, which again is 3 to the 6th power. Then we're going to have 3 cubed, which is the same as its original form. The whole thing squared. Now, inside the parentheses, you have common bases raised to exponents, and you're multiplying. So you can keep the bases and add the exponents inside the parentheses, and then after that, you can apply the power of the power rule. So you can multiply by the exponent that's on the outside of the parentheses. Okay, I'm going to give you 1 more minute, and then I'll give you the solution. Okay, so get some more room here. In the numerator, oops, excuse me. So in the numerator here, we can add the exponents, keep the base, which is 3, add the exponents, so this is going to be 3 raised to the 5 plus 6 power, quantity raised to the 3rd power. In the denominator, keep the base, so we still have 3. The exponents here are 6 and 3, so we're going to have 6 plus 3, quantity raised to the 2nd power. 5 plus 6 is 11, so we're going to have 3 to the 11th power, quantity raised to the 3rd power, divided by 6 plus 3 is 9, 3 to the 9th power, quantity squared. Now you have a power of a power, so you can multiply. 3 to the 11th quantity raised to the 3rd power is going to be 3 to the 11 times 3 power, which is 3 to the 33rd power, over 9 times 2 is 18, which is going to be 3 to the 18th power. And then when we have common bases raised to exponents and we divide, we can keep the bases, subtract the exponents. So this is the same thing as 3 to the 33 minus 18 power, and that's going to be 3 to the 15th power. If you have any questions, then please let me know. If you need me to scroll up, or if anything doesn't make sense, then please let me know. Also remember that if you see any question that you want to see another example of, if we don't get, if we have enough time after we get through the original 11, then I'll take any recommendations. Otherwise, let's look at number 3. So number 3 says, if 2 over 5 times x plus 3 over 15 times x plus 7 over 25 times x is equal to 2, what is the value of x? I'll give you 2 minutes and then I'll give you some hints. Okay, so this problem would be rather complex if you tried to go about it by finding a common denominator, evaluating the fractions into the common denominator, or converting them into the common denominator, adding them all up, and then ultimately solving for x. But you could do that. Remember, though, that the LCM, the least common multiple, is a really useful, practical. Those are synonyms of each other, and that's redundant, so I'm sorry. Though it's a very practical tool in order to simplify out a lot of needless denominators or a lot of nasty fractions. If I were to multiply on both sides of this equation by the LCM of the denominators 5, 15, and 25, and remember, if you do it to the left-hand side, you have to do it to the, sorry, if you do it to the left-hand side, you have to do it to the right-hand side, which is the 2. If you multiply both sides by the LCM, that's going to eliminate all the denominators, and it'll turn your whole equation into nothing but integers. So all the coefficients will be integers rather than fractions. So remember, to calculate the LCM, factorize each term that you're trying to, that's in your set of values. So we're trying to find the LCM of 5, 15, and 25. 5 is prime, so you can't factorize that any further. 15 you can break into 3 times 5, both of which are prime, so you can circle and stop there. 25 breaks down into 5 times 5, which are both prime, so you can stop there as well. When calculating the LCM, you take the product. Remember, product means multiplication. So you multiply all of the factors together, taking each factor the most number of times it occurs in any one factorization. So just to remind you, this gets tricky for students. This is one factorization. That 5 is one factorization. That 15 is another factorization. The 25 is another. There's a third factorization. So we're going to go factor by factor and, factorization, well, both. Factor by factor and factorization by factorization, counting up how many times each factor occurs in any factorization, and then take the largest of all of those values. So for example, 5 in the first calculation, the first factorization, 5 is used once. In the second, in 15, it's used once. In the third, for 25, it's used twice. So 2, or twice, is the most number of times 5 is used in any factorization, any one factorization. The common mistake here for students is to just take all of the factors, so they would take 4 5s because there are 4 5s in all the factors, but you have to think that the 2 5s from 25 already take care of the 1 5 that each other factorization requires. So the third factorization's kind of satisfies the other 2. So 2 is the most number of times 5 is used in any one factorization, so I'm going to take 2 5s. Now I only have to consider 3. 3 is used 0 times in the first factorization, 1 time in the second factorization, and 0 times in the third factorization. So I'm going to take 1 3. 5 times 5 is 25. 25 times 3 is 75. So the LCM of 5, 15, and 25 is 75. That means 75 is the smallest number that 5, 15, and 25 can multiply into directly. So I'm going to give you one more minute. I would recommend that you try and that you multiply on both sides by 75 to eliminate those denominators. And let me just rewrite, pick another color. It's not really another color. This one. Okay, so 2/5 x plus 3/15 x plus 7/25 x is equal to 2. So on both sides, just multiply the whole thing by 75. But make sure that this 75 gets distributed. And remember, you can think about 75 as a fraction as 75 over 1. All right, if that makes it easier. but make sure you take that 75 over 1 to each of the fractions inside of this parentheses. Okay? Actually, I'm going to give you 2 more minutes because that's a little bit of a process, and then I'll give you the answer. Okay, so multiplying on both sides by 75, we're going to get 75 times 2. Remember, the 75 you can write as a fraction as 75 over 1. So the 75 is only going to affect this 2, this 3, and that 7. It's not going to affect the denominators at all, but it's going to create a number which is divisible by the denominators of 5, 15, and 25. And these will ultimately turn into whole values. It's just a little bit easier to work with. So, applying this within the parentheses, we'd have 75 times 2 is 150. So you get 150 over 5x, plus 75 times 3 is going to be 225 over 15 times x. And then we have 75 times 7, which is 525 over 25x, is equal to 2 times 75 is 150. So now, notice 150 is divisible by 5, that's 30. So this thing just turns into 30x. 225 divided by 15 is 15, because 15 squared is 225. And then 525 divided by 5 is going to be, excuse me, divided by 25, not 5. 21. No, that's not right. Yeah, 21. Sorry. So this guy's going to become 21x. And that's equal to 150. So 30 plus 15 would be 45. 45 plus 21 is going to be 66. So we have 66x is equal to 150. And so dividing by 66 on both sides, we'd find that x is equal to 150 over 66. That's the same thing as 75 over 33. Which, can we reduce more? Yeah, that could be 25 over 11. So they're both divisible by 3 as well. So your answer would either be 25 over 11 or if you evaluated it, you could have also gotten 2.27, about 2.27. If you got any of those values, then I'm absolutely happy with that. Okay, if you have any questions, then please let me know. I'll also try not to use that color again because you can't really see that well, so I apologize. Okay, so 4 and 5 abide by the following definition. So this is one overarching definition for the next two questions. So for all positive integers of A hashtag represents the number of odd multiples of 3 less than A. Okay, so they're giving you this weird symbol, these two hashtag symbols next to a variable that at some point is going to represent a number. When they do this, they're telling you that it no longer represents the value of that number. It represents the number of odd multiples of 3 less than A, or less than that number. Number 4 is asking, what is the value then of hashtag 12 hashtag? And number 5 is asking you to evaluate the value of hashtag 35 hashtag divided by hashtag 17 hashtag. Okay, so I'm going to give you 3 minutes, and then I'm going to give you some hints. Once you get the process, though, it's pretty easy to evaluate, but it's just the interpretation is the real tricky part here. How to apply this definition to the actual problems once they insert numbers. But I'll give you 3 minutes, and then I'll give you some hints. Okay, so first of all, in the definition, they tell us that a has to be a positive integer. Okay, and then we're talking about evaluating the number of odd multiples of 3 less than a. So there's a bound. Whatever a may be, there's a bound between a and 0, because a has to be a positive number. Therefore, we're not talking about numbers less than 0. Okay, that's one thing. So when we're trying to evaluate, and actually let me just move 5 out of the way here for now. Let's move that guy down here. So for 4, what's the value of hashtag 12? Well, if we start just listing out, the whole definition is based on the characterization they supply, the odd number, or the number of odd multiples of 3 less than a. So we're talking about multiples of 3, and not all multiples of 3, but the odd multiples of 3. So just start counting by 3. We have 3, then we have 6, but 6 is even, it's not odd, so we're not going to count it. Then we have 9, then we have 12, 12 is even, so don't count it. 15, 15, then 18, but 18 is even, so it's not odd, so we don't count it. 21, then 24, but don't count that. 27, 30, 33, 36, 39, and then we'll see if we need anything less. But so far we have anything more, rather. But so far we're only evaluating hashtag 12 hashtag. So if we're at 12, 12 would be right here. There are 2 factors, excuse me, 2 odd multiples of 3 that are less than 12. 3 itself, which is 3 times 1, and 9, 3 times 3. So the answer to number 4 is 2. I'll give you one more minute to evaluate number 5. Okay, so if we look at number 5, we have an expression here of hashtag 35 hashtag divided by hashtag 17 hashtag. So first of all, I'm just going to write this vertically first, because in math that helps us. It's usually how we do division, not horizontally any longer. So if we were evaluating 35, 35 would be right here. So we would have 33, 27, 21, 15, 9, and 3 are all multiples of 3 less than 35. So that would be 1, 2, 3, 4, 5, 6 values. So the numerator would be 6. If we're at 17, now we would be right here. And so we have 15, 9, and 3 are as all multiples of 3, odd multiples of 3 less than 17. 6 divided by 3 is also 2. So the answer to 4 and 5 were both 2. If you have any questions, then please let me know. Otherwise, let's take a look at question number 6. So question number 6 says, Anthony has 2 timers. The first beeps every 12 seconds and the second beeps every 35 seconds. If the beepers start at the exact same time, how many times over the next 3 hours will they beep together? So just a little preview, you're going to have to turn hours into seconds, right? Because they give you rates in terms of seconds, beeps per second, or seconds per beep, I should say. And then they give you a total allotted time in terms of hours. So you're going to have to convert that into seconds. That's a little hint for you as well. I'll give you 2 minutes and then I'll give you some hints. Okay, so remember there's 2 steps here. One, we need to find the LCM of these 2 rates of beeping, because the lowest common multiple between these 2 rates would represent the rate of simultaneous beeping, or them beeping at the same time. Then we also need to convert the total 3 hours into seconds, because we want to be able to compare apples to apples. That's metaphoric, obviously. But in the way that we have information that's given in terms of seconds, or a rate in terms of beeps, seconds per beep, but we have a total allotted time of hours. So first let's find the LCM. We have 12 and we have 35. 12 can be broken down into 3 times 4. 3 is prime, so we can circle it and stop. 4, however, can break down into 2 times 2. 35 breaks down into 5 times 7, which are both prime. So this is the rare occurrence that they don't share any factors in common. So actually the LCM here is exactly equivalent to just the product of the 2 values of the 2 rates. So if we were to multiply, this is going to end up being just 12 times 35. But I want to make this point here that oftentimes, if you don't go through the process of actually calculating the LCM, you're not going to find the smallest multiple. The product of 2 or multiple values will always be a multiple of those values. That's by definition. If you multiply 3 values together, the result will be a multiple of all of those numbers, right? That's I think pretty naturally understandable. However, there could be a number that's smaller than that product that all of those values can still multiply into. And if you don't capture that value in your calculation, or if you don't use that value in your calculation, you will get the answer wrong. So here, the LCM is just going to be equal to, well, if we go through it, notice 3 is only used once in the first, so we take 1, 3. 2 is used twice, only twice in the first, and 0 times in the second, so we take 2 2's. 5 is used once in the second factorization. Excuse me, I think I was saying the second. 3 is used once in the first, 2 is only used twice in the first, 5 is only used once in the second, 7 is only used once in the second. So you can see that it basically takes all of the factors that define the composite numbers that you began with. So it's exactly the same thing as just multiplying the numbers together. So if we take 12 times 35, we get 420. So what does that mean? That means that every 420 seconds, and only every 420 seconds, will all of those both of those beepers beep together. So that's my first kind of step for you, or hint. Next, we also need to convert, let's see, they say 3 hours into seconds. Sorry, let me get some space here. So what I'm going to do is I'm going to start excuse me, with 3 hours. It's my given unit. It's my given amount of time that I want to convert. It's not written as a fraction, so I'm going to go ahead and write it as a fraction by just putting it over 1. And I'm going to multiply by some equivalent value to 1. Okay, some value that represents 1, or what you evaluate into 1, in order to eliminate the hours and go to another unit. So I'm going to go from hours to minutes. I have hours in the numerator already, so I'm going to put 1 hour in the denominator of the fraction. In the numerator, I'm going to put 60 minutes. Notice how 60 minutes is 1 hour. So this is something divided by itself. So 60 minutes, even though it's in different units, 60 minutes divided by 1 hour is 1. It's something divided by itself. So 1 times anything is still that same something. So I'm not changing the value of 3 hours. I'm only manipulating the units here. Because when I do this, notice that hours will cancel with hours, and I'll be left with an answer in terms of just minutes. But I don't want just minutes, I want seconds. So you're going to go one more round. I have minutes in the numerator, so I want 1 minute in the denominator, and I know that there are 60 seconds in 1 minute. So now when I multiply through, minutes cancel with minutes, and I'm left with an answer in terms of seconds. This is really useful to check in the problem-solving process that you haven't made a mistake. If your units come out wonky, like you get something like seconds squared over meters, I mean, maybe if you're talking about a specific problem, that could make sense. But usually if you're asked about time and you get something like seconds squared over feet, that's not time. It has time in it, but that's a unit that is much more complex than just some function of time. Okay, so I'm going to give you 2 more minutes, and then I'll give you the solution. Just try and make sure you can see everything there. Okay. Okay, so our LCM, or simultaneous rate of beeping, is 420 seconds, meaning every 420 seconds both of the beepers will beep together. And if we calculate how many seconds are in 3 hours, we just need to multiply all across here. And so we end up with just 3 times 60 times 60 seconds. 60 times 60 is 3,600. 3,600 times 3, is that 10,800? Let me just check that. Yes, 10,800. So we have 10,800 seconds in 3 hours. So if we take that 10,000, or those 10,800 seconds, and I divide by 420 seconds per every one beep, because every 420 seconds and only every 420 seconds do we get a simultaneous beep. Now we can solve. So what makes this hard, and a lot of students get intimidated by this, is that this value right here, the numerator, is written as an integer, whereas the denominator is written as a separate fraction. So to deal with this, just rewrite the numerator in terms of a fraction. So we could say that this is 10,800 seconds over 1 divided by 420 seconds over 1 beep. Now we have a fraction divided by a fraction, which we have a process in order to solve. So what you do is you keep the numerator the same. So we're still going to have 10,800 seconds, I'm going to abbreviate it, over 1. But then change the operation from division to multiplication and take the reciprocal of the denominator, meaning you flip the numerator and denominator of the bottom fraction around. So instead of, instead of 420 seconds over 1 beep, I'm going to multiply by 1 beep over 420 seconds. Notice that seconds will cancel with seconds, and now I'll have an answer in terms of beeps, and that's exactly what they asked me for. They asked me how many beeps over the next 3 hours, how many times will they beep together, or in other words, how many beeps will you hear, simultaneous beeps will you hear. So multiplying, we just get 10,800 over 420, and this is in terms of the units of beeps. And so our answer, when I do that division, I get 25.7 if I round. You have to be able to interpret this answer. 25.7 means that they are going to beep simultaneously within 3 hours 25 complete times. And they are 0.7 towards the next simultaneous round of beeping. 0.7 is a decimal, but as a percentage, that would be 70%, right? A 0.7 would represent 70%. So you can think of this more as in its statistical nature, that it's of a whole value. So the 0.7 you have to be able to rationalize. That hasn't happened yet. It's only until it gets to 26, because enough time has not elapsed for it to get to the 26th round of simultaneous beeping. So that 0.7 there is meaningless because it hasn't happened yet. That 26th beep, simultaneous beep, hasn't happened. So it doesn't matter how close you are, at that 10,800th second, you're cut off because that's the end of 3 hours. Okay, so the answer here should be 25. If you have any questions, then please let me know. Otherwise, let's take a look at number 7. Number 7 asks, what number less than 100 has a remainder of 2 when divided by 2, 3, 4, and 5? So what number less than 100 has a remainder of 2 when divided by 3, 4, excuse me, I keep on messing that up, 2, 3, 4, and 5. There's 4 numbers there. I'll give you 1 minute and then I'll give you some hints because this problem seems a lot trickier than it is. So I'll give you 1 minute and then I'll give you a hint. So the remainder part of this problem is really tricky, and it's really not as hard to deal with as it seems. What I would recommend is instead of trying to find a number less than 100 that has a remainder of 2 when divided by these 4 values, 2, 3, 4, and 5, instead find a number that is exactly divisible or is a multiple of 2, 3, 4, and 5, or in other words, is the LCM of 2, 3, 4, and 5. If you then want a number that has a remainder of 2, you would simply add 2 to that number. Because if that number is directly divisible by all of these other 4 numbers, then that number has a remainder of 0 when divided by 2, 3, 4, and 5. So if you calculate the LCM, which by definition is divisible, so it has a remainder of 0, then you would merely add the remainder that you intend, or that you're looking for. So if you're looking for a remainder of 2, you would add 2 more to the LCM of these 4 values. Okay, I'll give you 2 more minutes, and then I'll give you the answer.